So my name is Pankaj. I work at Samsung, and today I'll be talking about block atomic rights. I know the audience is a bit like, not everyone knows stories that much, so I try to make it more generic. So if you're an expert in these topics, if you sleep, I don't mind. It's more for, like more general audience, and there are some storage experts here, so maybe they'll not get a lot out of it. But yeah, so let's start. Before we go any further, like let's try to talk about what is block atomics. You can think of it like when you have a CPU instruction, like when you have like when you want to do something atomically in memory, it's you can think of the parallel for that in storage. So what it means is it's either in or not. There is no partial state possible when you have atomicity guarantees. So as I written here, like you don't have there's no possibility where you can have tone rights that goes to the device. For example, in this picture, you can see like first we have like in gray color you can see the old data, and let's say I do an I/O of 16 KB in this example, without atomicity guarantee. If the power goes off, let's say suddenly someone pulls the plug, there is a possibility where you can end up in a state like this, where like there's partially the new data and there's partially the old data, which some systems are developed to like be robust against it, but they have to do a lot of things to make sure they can handle the situation. But if you have like something like atomicity guarantee, then it's either the old data or the new data. It's never in between, whatever happens. So in this talk, I'll be using a lot more of NVMe stuff, but block atomics itself is not really tied down to NVMe. It's like a storage thing. Like SCSI also offers atomic rights guarantees, and it's not specific to NVMe. But I know a lot more about NVMe, so I'm going to use that as an example here to illustrate what it means. So NVMe has there are a lot of parameters around atomics, but things that are useful to us for this talk is the boundary information, which is this acronym, how you want to call it, and then you have another one that says that gives a hint on what is the size. So these two defines the boundary and the size constraint when you want to do something atomic. In NVMe, I don't know if it's a good thing or a bad thing, but we have this implicit atomicity. So if your device supports atomic rights, then you don't need any special command, unlike SCSI, where you have to say, hey, I want this right to be atomic. In NVMe, like the device sees, oh, it's actually aligning with what is supposed to be atomic, and it does things automatically to the device. So it's a spec, and yeah, so that's what it is. For example, in this case, you can see that if you send let's say you're doing write A, write B, write C, those things will go atomically. But for example, if you do like write D, then the point is within the boundary. It can be still atomic, but there is no guarantee that the whole thing is going to be to the device. Okay, so I explained what is block atomics, but why do we even need something like block atomic in a device? So I'm going to give like a specific example of like why we need something like block atomics for storage devices. The primary user of something like this are databases. Databases, as you know, they try to store data, and they want to make sure that it's reliably, and they can always get the data back, whatever they have written. So, and databases usually work in a bigger page size. Like they have blocks that are usually bigger than the page size of the device itself. I'll give an example for Postgres. It has 8 KB. So without something like atomicity guarantee, you can't be sure that when you do a write of 8 KB, it's going to go to the device without like, in most cases it's fine, but let's say power goes off or something like that, then if you don't have other power protection, then it might end up in a in-between state, which databases don't like at all, because then it's a corruption and it's very hard for them to recover back from that corruption. So, okay, so 5 minutes. So Postgres, like usually what they do is like, because a lot of devices don't offer atomic guarantees, they have a mechanism called full page writes to overcome this whole situation. So what they do is every time they do a checkpoint, let's say it starts from a clear state, and you change a certain page of the database, then what they do is like they compress the page and write it to the write-ahead log once, and then it's also written again without compression to the actual BT, or like actual data itself is being processed. So you can see, like, to circumvent the issue of atomics, many databases, they resort to writing it 2 times instead of just once. So yeah, so it's in Postgres it's called full page write, and as you can already see, the problem is if you're writing it 2 times, then the device is going to wear off quickly, and like you're utilizing the bandwidth for writing the same thing again and again, and etc. etc. So let's assume a world where, like, right now Postgres doesn't support atomics, but let's assume, like, just for funsies, like Postgres offers it, so I turn off the full page write. So there's a toggle in Postgres where you can say, hey, I don't want full page write, just like go with it. So as you can imagine, like the performance considerably increases when you turn off the full page write, because you don't have to write it twice, you write it only once, which is nice. And also the write amplification reduces, like, you don't do a lot of updates, and overall the device is going to see much less writes. This is more like application WAF. I'm not talking about, like, if you go into details, it's not the storage, but I'm talking about from application side of view, like you don't write it twice, so which is great. And one thing that came after a lot of discussion is, like, this is which was also new to me, was savings in archival storage. So like I will talk about more in detail about this point-in-time recovery. Like, I have like 2 more slides about describing why it's a big issue. But the point is, more than the performance, like the database people really care about the recovery part. Like, if they want to, if they do full page writes and they have put everything in the logs and they have to back up the log, and that can take up a lot of space, and these things go to like slower devices, and you also spend a lot of money in just saving them. And also, like, the same thing is applicable to when you have replicas of the same databases, where you have to pass on the write-ahead log to all the replicas. Then it's the same problem. Like, you have to spend a lot more data. I can also show about, like, there'll be a slide about like how much the effects can be when you don't have full page writes. So how point-in-time recovery works? Like, I mean, it's pretty obvious what point-in-time recovery means. Like, Postgres has this feature where, like, let's say I want to go back to the state where this, like, the database instance was like on this date, then it can actually roll back to that point, and it's actually important for, like, banking and governance stuff. They really need this kind of feature in the database itself. So typically what happens is, every time you do a checkpoint, like, every time I say, okay, this is the new reference for the database, you actually just recycle the write-ahead log if you don't have any archiving. But because you need to go back in time, you want to have, like, you want to have the point in the recovery. So people enable something called continuous archiving. So what it does is, instead of like recycling, before you recycle the val, you just store it in a different place, and then just keep going on. As you can see, we just go on and on, and then archival is going to just, like, keep copying that in a different space. And whenever you want to restore the database, you use the archive logs and the base backup, and then you can basically go back to that point in time. So I did a small experiment, like nothing fancy, just a PG bench workload for some time, right? So when you have full page writes enabled and when you don't have full page write enabled, you can see the val can just like explode like crazy. So if you don't have continuous archiving, it's not a problem because you're going to recycle things, so things are mostly under control. But if you want to save this thing for future recovery, it's going to add up pretty quickly. So I hope I've convinced why we need. So this is very specific to what I've told is specific to Postgres, but MySQL also has like they do. They have tone rate protection is a bit different than how Postgres does, but they also have double writes, and they can actually, they don't have to do a second write if atomics are enabled. So yeah, but they have a different architecture. So it's not really applicable, whatever I said, for MySQL, but they also have benefits from having something like atomics. Okay, so this is like the overall view, why we need something like this. Now I can go a little bit into how it's, like been implemented in the kernel. So as I said, like we have two parameters that are that whenever a device is attached to the kernel, we read these two things. That's the nowpf, like it's I don't know the abbreviation. It's like namespace atomic write unit power fail. And you also have NABSPF. I think it's something with B is boundary. I don't know. So yeah, boundary size power fail. Yeah, A is atomic, N is namespace, B is boundary. I don't know what S is, but maybe size, boundary size. Yeah. So you have now PF and NA. So at least the driver right now, like we don't. There are a lot more parameters, but at least the kernel driver right now in NVMe like really cares about these two things. And there are some features that we don't support because it doesn't make sense to do it in the kernel, which I'm not going to talk about. Okay, so once the driver exposes, hey, these are two things I support, then the NVMe driver comes in and actually reads those values and puts it in these variables in the NVMe driver itself. So you have like hardware max, boundary, unit max, and unit min. There are like slight differences like between hardware max and unit max. Like this is always needs to be power of 2. This doesn't need to be, but the basic idea is like you use those two values to derive your boundary, and then you use the size to determine how much your size of your atomic writes can be, and the atomic unit minimum is based on your logical block size, because devices when the logical block size is supposed to be atomic. That's sort of the guarantee they give. So then what happens is like block layer is like, oh, okay, you support atomics, let me, so that's also the point, right? Like here, it doesn't need to be NVMe, it can also be SCSI. So they all report this value back to the block layer, and the block layer sort of transparently exposes it to the user space, like what you support as for atomics. Here, block layer reads those things again, and then it adds a bit more of nuance over here. Like block layer has to also make sure that when it sends an I/O, the I/O should not be split for atomics. So typically, when you do I/O of like let's say 1 MB, you do DD or whatever, copy something. When you submit like a 1 MB I/O to the block layer can actually split the I/Os based on different conditions. But when you want the I/O to be atomic, at no point in time it should split. And also there are a lot more restrictions, like about like how many segments can be, and et cetera, et cetera. So like there are more nuances, but the point over here is block layer does recalculation on whatever the device exposes, and then caps it to a place where it's for sure can submit like a single BIO to the device, and the BIO will not be split at any point in time, because that's sort of the guarantee you give to the user space that, because if the BIO splits, then what happens, like one BIO goes in and the other one, like power goes off, then you're basically like not giving the guarantee of atomics. So the block layer reads this, and then finally to the application, the application can do a static call, like a syscall, to know what is the max and min I can actually use on the block device or file system. Right now we only support a single segment. I will talk a little bit more about this, but the point here is like there were different choices that had to be made to guarantee that the bio that you submit to the device cannot be split. So that after seeing the trade-offs, like finally the community settled on, okay, let's stick to one segment when we want to make sure that the I/O is atomic, and yeah, so that's where the whole limitation comes in segments. For segments, for people like, if you in user space terms, if you do a P write, you can have like multiple vectors, like IOVs. You can actually gather multiple of them. And but if you want it to be atomic, then it can be only one vector, like one IOV. So what user space can do? It can now there's a new flag in the kernel, like you have to do P write v2, RW for atomic, and like if you're within the boundaries, then yeah, things should go pretty smoothly. So just to recap, the constraints are like, the length should be power of 2, and it should be like the IO length should be between the min and max guarantees that the IO gives, and also there's also the boundary limitation, like you can't really cross the boundary, like let's say the boundary is like 16K, then you can't set an IO that sort of straddles the boundary, and so those things also need to be taken care of. And as I said, like only single segment is supported for now, and it's only direct IO. This is very important because I'm going to come to it later on. So right now we only support the atomics only through direct IO. For the kernel itself, kernel will make sure it doesn't merge atomics, that it cannot guarantee that it can go to the device in one IO. So for example, if you send two IOs and if it straddles the boundary of the atomic itself, then it's going to be like, okay, I'm not going to merge it, just send it as two different IOs. So, and it'll always make sure it doesn't split the atomic writes. So this is how, like, until now I've talked only about the block layer, like how things are, plumbed. And now let's talk about file system. Any questions so far? Like, is it too boring? Is it any questions? It's fine. Okay, have everyone with me. Cool. Yeah, it's not very flashy like networking or something, right? Like it's block and it's slow, and but it's fun for us who are working on block layer. But yeah, cool. File system support. So at this point, we have only ext4 and XFS that supports atomics, and it's only through the direct IO path. And both ext4 and XFS supports like single or multiple blocks atomic. So I will explain more in detail what it means, and but ext4 has this feature called big alloc. We don't basically the idea is if you enable big alloc, instead of having a file system block, you can set the cluster, so it considers a cluster as a block. I have to go in detail to explain what it is, but you can think of it as like you sort of like you reduce the metadata overhead, but the ext4 itself uses this feature to layer in the atomic support on top. But of course, XFS does it differently. So XFS supports both single and multi, but it uses reflink. It's a copy on write mechanism that's an XFS as a fallback if it cannot really if it cannot do the I/O in atomic fashion. So these things. So for the XFS part, I will go into more in detail. ext4, I think it will be too much for this talk. So I will talk more about XFS, how it's implemented. So small step back. What is what is the FS block? I don't know. Maybe I'm going to a simplistic view, but I don't know the audience, so I try to make it as generic as possible so that more people get something out of it. So what is a FS block? It's like you can think of it as a page for memory management. FS block is like a minimum unit of data allocation in file system. So whenever it allocates a block, it's going to be in block. It's always FS block sized. That's the minimum that it always allocates. And extents, like most of the file systems nowadays are extent based. So it describes, instead of saying block by block, you actually say, oh, I actually represent from, you can, reduce the metadata by actually saying the extent represents from 0 to whatever, a bunch of blocks together, and it's just one extent. And mapping, so files, so this is all in it's your abstraction in VFS, and then ultimately whatever FS block is what goes to the device itself, and basically files are represented as multiple blocks that are going to the, and mapping sort of holds the, what file system does, it has a mapping to have logical to physical locations, and that's what the mapping is for. Yeah, the reason I talked a little bit about what is FS block is because I'm to explain this, right? So initially, when XFS added atomic support, it was only for a single FS block. The point being, you want to make sure that the block size is within the minimum and maximum. And once you do that, then via statics, the XFS will say that block size is my maximum and minimum atomic size that you can do. So this was the initial support that was added when atomics came out in 6.13, not too long ago. But the point is also, at that point, XFS also supports larger file system block sizes. So if you want to increase the atomic granularity to bigger sizes, then you can actually use a large block size to leverage the bigger atomic sizes. But the point is, not everyone wants to reformat their drive to move to bigger block sizes. So the work continued on to add large atomic support. So if you want to have a large atomic support for file systems, then the file system needs to guarantee that it can get an extent that are contiguous and also aligned to whatever the atomic granularities and atomic sizes are. For example, let's say the maximum atomic size is 4 FS blocks, and I'm trying to do an IO of maximum atomic size. Then the file system allocator, that actually allocates the physical blocks on the device itself. It goes in, tries to search different groups and try to find things that are contiguous and nice that can align with whatever atomic guarantees needs, right? But what if your file system looks something like this? The red color means it's already been used. Let's say your file system is extremely fragmented. Then there's no way you can actually get extent that is actually aligned to your atomic boundaries and the atomic constraints, right? So we either have to say to user space, hey, you know what, I can't do any more atomics anymore, or you should have some sort of a fallback mechanism to deliver your promise. Yeah, similar to something what they said in IO during zero copy. You try to do zero copy. If not, you have to always fall back to something that can be bad in performance, but it sort of it doesn't. You don't have to go on giving error to the user space saying, hey, I can't find an extent. Sorry. So before going into how the atomic support has been implemented, a small tangent on the reflink of XFS. So XFS has this feature called reflink. It's basically when you do CP reflink base image copy image, it's pretty instant because it's a metadata operation. It doesn't actually copy stuff. What it does is it goes to the file system and be like, hey, you know what? Both are copy. Try to share the blocks. So you can see here file A and file B. File B is a clone of file A. Then you share these logical blocks in the device, and physical blocks in the device itself. So you don't have to copy it for no reason, right? So the reason I'm talking about this is this is very critical for having the large atomic support later on that I'm going to talk about. So why is it useful? It's used for snapshotting, deduplication, and a lot of use cases for this. But we also leverage the reflink capabilities to use as a fallback. So let's say our in a simplistic view, this is how the layout looks like. then what what the copy on write fallback will do is like, whatever extents you have, I'm going to just I'm not going to be a chooser. I'm just going to choose whatever I can as best as possible. And the key thing is like when it does a once it so and the key thing over here is like when it commits, it's always one atomic commit that it does. So the user space never at any point can see the in-between data. So this is a fallback when we do there are also other cases, but mainly if your file system is fragmented and if the file system cannot find extents that are contiguous, then it will resort to something like copy on write. So here you can see first we try to allocate blocks in IO map begin. It's like an internal function that we use. So if it cannot allocate contiguous extents that matches the atomic guarantees, then I'm gonna go and do the curve fallback, which is gonna pick whatever it can, and it does the write. It submits the it submits the BIOS itself to the place. And once everything is over, there's going to be one transaction that remaps and says, you know what, now this is your new data. So of course, this is slow. This is not like hardware accelerated. Like if you have hardware that supports it and if you align things, then it's like perfect. But this is sort of a fallback that happens when things are not good. Yeah, okay, so this is all I had for the file system support. So I have like 15 minutes more, 20. Yeah. I can go a little bit on what are the future work in this area. So Postgres is one of the major databases that still uses buffer IO. I mean, they had their own reasons why, like most databases these days use direct IO, but they still support buffer IO. They did add like an experimental direct IO support in Postgres, but there's still time for it to become like really mature in that sense. Just show of hands. Everybody knows what's a buffer IO and direct IO, right? Like I hope I'm not. Does everybody know? Most people know. Okay, so buffer IO is you always talk like when you do a buffer IO, it goes to the page cache. Like that's the cache you have in your Linux offers like a page cache. It first goes there, and then after some time, a write back comes and actually write those pages in RAM to the disk. It's sort of to speed up operations. Direct IO is something that you have in the kernel that bypasses everything and goes directly to the device. So so Postgres until now, Atomics is only supported for direct IO, but the future work is like we're gonna add like hopefully the buffer IO Atomics. But I also tell what are the pitfalls and try to talk about the whole thing over here. But again, coming back to Postgres, like the common deployments for Postgres is like small setups, like and I'm pretty sure many people here run their own home lab, and I use a lot of Postgres in my home lab. It's not like I have a server farm or anything, pretty small server, but it does the job. And sometimes it's a part of a larger application, but it's not the main application itself. And like there are also cases where these hosting services company where they intentionally overcommit because they know not everyone is going to use it at all times. So that's also a common deployment scenario for Postgres. So even though Postgres has the direct IO support, the point is it may not be really universally adopted in the future. And one of the Postgres developers that we are collaborating with, like he was telling that he's the one who's also doing the work on direct IO. He said even though direct IO might be an alternative, but he doesn't see it being the predominant one for Postgres in a long time. It'll still be, most people will still use buffer IO. Because if you think about it, like if you I think the next one explains it a bit better. So when direct IO makes sense is when you have like a dedicated server that's just doing Postgres or like some database, and it has all the memory it wants, it can do whatever it wants. But if you go to other places where like the database is used as a part of the application, usually all the databases, they have like a small cache, like a buffer pool they call. So if you want the performance of a direct IO to be really good, then you should have a really large buffer pool. so that you can cache in all your reads and writes and everything. So it can be really fast. But let's say you have you're running a service company, Postgres is a service company, and then you have like a lot of databases, and it's very hard to say how much buffer pool you should give for each one. So you would rather delegate that responsibility to your page cache. It can act as a way to amortize the cost, instead of saying, okay, I'm going to give so and so to the database itself. So whenever you have like a lot of DBs running simultaneously together, then it makes more sense not to use direct IO in Postgres. And if you're using a lot of if you have a dedicated if you have multi-tenant system, it's better not to use buffer IO. It's better not to use direct IO in Postgres. If you're like having a single tenant that's just doing one thing, then direct IO might be the best option for them. So in the kernel, what are the problems to upstream this support? Is this is a small one. When you copy stuff from the user space to the page cache, there are cases where you can actually stop doing mid copy. Let's say you're doing atomic IO and it's going to the page cache, and the page cache has to copy from user space to the page cache. There are possibilities where you can just do half of the copy and then you can just go back. And that is not good, because if you want it to be atomic, the whole thing needs to be copied. So this has a lot of solutions. It's not a big deal. I think the biggest problem the community had was the model itself. As I told, in buffer IO, you write something to the page cache, and the write back thread comes much later on, and it can evict the pages and send it to the device itself. And it doesn't really fit the model of how atomics and write back model works in the kernel. So the community came up with something really nice. I would say it's like super smart. There are talks now to add a new flag in the kernel called RWF write through. So basically, what it does is, you can see my amazing diagram here. When you a normal buffer IO, what it does is it goes to the page cache, write back thread comes later on and flushes whatever, it evicts stuff from page cache and writes to the device itself. But with write through, what we do is we write it to the page cache, and we immediately do a direct IO, IO to the device itself. So you can think of it as like a desync, where you do where you write to the page cache and do a sync, but without the data integrity guarantees. What I mean by data integrity is sometimes when you write something to the device, it doesn't mean that in computers, a lot of things lie to each other, right? So the device, when it says the IO is okay, it doesn't mean the IO actually went to the NAND itself. It probably went to the RAM of the device. So when you use something like desync, you want to it makes sure that the whatever is there in the RAM of the device goes to the NAND. But not all applications need that guarantee. Some of the some parts of Postgres need the guarantee, so they want to use rdesync. But some of the parts of Postgres doesn't actually need the guarantee, so they can use something like write through. So the plan is to first add the write-through support, and write-through is actually useful irrespective of whether there's going to be atomics on top of it, because right now, for example, Postgres does a p-write and then do a sync file range to make sure it goes into it persists to the device itself. Now they can just use something to write-through, and once it's called, and its life is better. So the idea is to probably add buffer IO atomics on top of write-through in the future. Okay, acknowledgements. So I'm just a messenger here. A lot of things I've helped in reviewing, but a lot of the work were done by people from Oracle and IBM, and Christoph is here, and they've given a lot of inputs on how the API should look like, and so really good stuff. I think that's all I had. So if anybody has any questions, that's it. I saw a lot of people sleeping, by the way. I have noted your names.
Is there any reason that it's not supported in BetterFS? It has the same sort of copy on write?
True. I have to look. I don't know why it's not there. Like I was also thinking when I was putting like why it should be possible to do. But ButterFS itself is like I don't think the databases use a lot of ButterFS, to be honest. Like because for them they don't like maybe they can use no curve mode, but like many databases use ext4 or XFS. So that was the main target when people added the support. But ButterFS can actually always do a fallback like how XFS does, like because it can atomically change. So maybe it's something to look into. But I don't know how many databases use ButterFS, to be honest. It has different use cases, but yeah, I'm not sure.
Yeah. I assume all this breaks if you have RAID of any sort, or
Sorry.
if you have any sort of RAID, mirror devices or something, does all this break?
Actually, I didn't get the question. So all this are RAID or like?
RAID, redundant array of inexpensive disks.
Like, so.
Or just mirrors, which is probably what you'd use, but.
Okay, can someone repeat the question again? Yeah, like that. I haven't thought about it. Yeah. Yeah. You have to make sure that things are always like. But does it matter because like when the file system, if it's suppose atomics, it's like you have.
So the file system will then go to the RAID device, and the RAID device will then go to the.
Yeah. I think we do. Maybe Christoph can answer. I think we do propagate the when you do RAID. So.
Yeah. Okay. Okay. This is going to be.
Okay.
It'll be hard to do atomics because you have to write across two devices.
Yeah.
And so you can do atomics on one device, surely, but on two devices, how would you synchronize them? No? All right.
So for simple RAID 1, it literally just works with all the other caveats of data atomacy of a simple RAID 1. So you'd actually need the bitmap tracking of which leg is valid in case of a failure. But otherwise, for RAID 1, it's trivial. It doesn't work for anything that stripes, so RAID 0 or parity RAID.
Good question.
Okay. Okay. All right.
Thank you.